Everybody, let us talk about multi-qubit quantum gates. To discuss multi-qubit quantum gates, we consider an eigenbasis set with four ket vectors ket00, ket01, ket10 and ket11. So therefore, this system will represent two qubits and four eigenstates. So it is a dimension 4 quantum system. And the standard basis vectors in this eigenbasis set are represented by these column vectors. The first gate that we will discuss is C0 gate. We are putting C0 in as a subscript of U. So U represents any unitary operation. Now this ket00 going to ket00, this actually represents the operation of the C0 gate. Now a C0 gate will have two qubits, one is control qubit and the other is target qubit. If the control qubit is 0, the target qubit will have no action at the output, but when control qubit is 1, the target qubit will be flipped. We will get the flipped version of the target qubit at the output. So that's exactly is being shown here. So in this 0-0 combination, the most significant bit represents the control qubit and the least significant bit is the target qubit. So that means the control qubit in ket00, the control qubit is 0. So when the control qubit is 0, the target qubit will remain as it is. So that's what exactly is shown here. Again, in the second combination, the control qubit is 0 and the target qubit is 1. Since the control qubit is 0, so no change in the target qubit. But let us come to the third combination. When the control qubit is 1, so definitely the target qubit will get flipped. So therefore the output will be ket11. Similarly, in the last case, when the control qubit is 1, the target qubit will be flipped and we get an output of ket10. This represents the explicit form of the C0 gate. This is the representation of the C0 gate in terms of the outer product of the respective eigenstates. And this is the representation of the explicit form using the identity and the poly X gate, because when you open this outer product, ultimately when you solve this equation, you will get this matrix. And this matrix, actually this is one only. So you will get this matrix. You look at the last part of the matrix, you will see that the last part is actually a poly X gate that represents the flipping operation when the control qubit is 1. In this case, we have only one control qubit, but we can have more than one control lines. So if we have two control lines, that means it will be a controlled NOT gate. So this gate will have three inputs, two control qubits and one target qubit. The target qubit flips when both control qubits are 1. So when both will be 1, only then the target qubit will flip. The explicit form of the CC0 gate is given by this equation. You expand this equation, you will get the unitary matrix for this CC0 gate. The CC0 gate is also known as the Toffoli gate. Very commonly and very famously, it is known as the Toffoli gate. This is the symbol of the Toffoli gate, where two control lines are there and one target qubit is there. Next, we will discuss the swap gate and the Fredkin gate. The swap gate acts on a tensor product state as. So what is the tensor product state? The tensor product state is the ket psi1, psi2. So there are two qubits. One is ket psi1 and the other is psi2. Once you apply the swap gate on this set of tensor product state, so what will happen? The state will swap itself. The swap will swap with each other. That means the output will be ket psi2, ket psi1. So this is the symbol of the swap gate. So you will see that after the application of the swap gate, you will see that the two qubits are swapped. The two qubit values are swapped. And this is the explicit form. Once you solve this explicit form, you will find the solve means when you try to put it in the in the matrix form. So let me show how can you expand this. For example, you have the first term, it is ket 00 bra 00. So this can be solved as, so ket 00 is represented by 1 0 0 0 and bra 0 0 will be represented as 1 0 0 0. So once you solve this matrix and you add all the other matrices, you will see that ultimately the matrix, that the output that will come is written here as the swap gate matrix. So that's the unitary operator used for the swap gate. Now we can also add a control line here. Adding the control line means you will when the control qubit is 1, only then the swap will take place. Again, this is the explicit form. Now we can have the controlled U gate. Now if you look at the C0 gate here, the last quadrant of the C0 gate basically is a poly X gate. So we can generalize the controlled, we can generalize this part and we can put any unitary operator. So that is why a gate is there which is controlled U gate. So controlled U gate may be a poly X gate or any other gate you want to, any other functionality that you want to implement. That can be done with that's just an expression of the generalized controlled U gate. The next gate I will talk about is the Hadamard gate. Hadamard gate is used to make and then unmake superpositions. So Hadamard gate can be used to generate the equal superposition states of the qubits. Now the matrix form representation of the Hadamard gate is given by this matrix, 2 cross 2 matrix. So this is a single qubit gate. Now once you apply Hadamard gate on ket 0, so if you solve this expression, you will obtain ket 0 plus ket 1 1 over under root. The normalizing factor is 1 over under root 2, and this particular state is also known as ket plus. Once you apply Hadamard gate on qubit 1, so you will get here a negative sign. So ket 0 minus ket 1 you will get. So you have to keep in mind, whenever you apply the Hadamard gate on ket 0, there will be a plus sign. Whenever you apply Hadamard gate on 1, there will be a negative sign. And this overall application of the Hadamard gate on 1 is termed as the ket negative qubit. Right? So the application of H on ket 0 is ket plus, application of H on ket 1 is ket minus. Now we have to actually extend the use of Hadamard gate on multiple qubits. So let us extend the application of the H gate to 2 qubits. Now this is represented by, so if you represent, how can you represent the application of H gate on 2 qubits? So this is the way how we represent it. This is H gate, this is the tensor symbol and 2. So this basically tells us you are applying the Hadamard operation on 2 qubits. So Hadamard gate with tensor product 2. So this tensor 2 on the superscript of H implies that we have to extend the Hadamard gate on 2 qubits. And this is what I have shown, the meaning of H cron 2. This is H superscript cron 2. If you apply H superscript cron 2 on ket 00 state, so this is the cron operation between 2 Hadamard gates, right? And this is the value. You can solve this H superscript cron 2 expression if you solve this part. So that will be given by this expression, this 4 cross 4 matrix, right? This 1 by 2 is basically, you will get from 1 by under root 2, 1 by under root 2. Once you multiply the 2, you will get it as 1 by 2. And since we are applying H superscript cron 2 on ket 00 state, so we have to put in the product this ket 0. This column vector is representing the ket 00 state. So once you solve this expression, you will see that this is the equal superposition of the 2 qubits. This is the output of the output of the Hadamard gate applied on 2 qubits. Now I have just given the second method to solve these expressions also. This is H superscript tron 2 acting on ket 00 state. So this can be separately written like this. And what is the meaning of H superscript tron 2 is that one H is acting on one ket 0 like this. So if you solve this, again you will get the same output as was in the previous method, previous case. Alright, now let us extend. So with the what we have seen, the application with the application of the Hadamard gate is that once you apply Hadamard on ket 0, as I have just now told you, that you have to remember it is ket 0 plus ket 1 under root 2. So there is a plus sign when you apply H on ket 0. There is a negative sign once you apply H on ket 1. So this you have to keep in mind, because we have to take care of this negative sign once it is applied on the on ket 1. So we have to be very sure about the sign of the numerator expression. Alright, so if this is the case, let us try to put these two expressions in a general form. So what we see here is that we are applying the Hadamard gate on ket x. So ket x is representing either 0 or 1. So x is a variable that gives us the if it is ket if we are applying it on ket 0 or we are applying it on ket 1. So if we are applying it on ket 0, so that means if you see here in this expression, x is on the exponent part. So 0 exponent will give this 1 here. So plus sign will remain as it is. But when x is 1, that means when you are applying Hadamard gate on ket 1, so that means here negative sign will appear. So this expression actually is the generalized form for these two operations. That means Hadamard acting on ket 0 and Hadamard acting on ket 1. Now let us further simplify the expression, like so this is the application of the Hadamard gate on a single qubit, right? So we are just trying to put a summation here. So what this summation will take care of? It will take care of ket 0 plus ket 1 or ket 0 minus ket 1. That's why this summation is there, right? And this minus 1 exponent x dot y will take care of the sign, right? So if you will try to expand this, you will see that either you will get this expression or you will get this expression if you expand this expression. All right. So this is the application of Hadamard gate, generalized expression on single qubit. But let us extend the same concept to 2 qubits. So this is H superscript tron 2 acting on a 2 qubit system. A 2 qubit system is represented like this also. This is a eigenbasis set for 2 qubits. These are the eigenstates mentioned straightway. This is the decimal form representation of the eigen values, and this x is basically x dot 2 this for the 2 qubits. X1 is 1 qubit and x2 is the other qubit. Now you pick the expression from here which is the Hadamard acting on 1 qubit. Here we are applying Hadamard on 2 qubits. So use this expression to write 2 brackets and 2 expressions for different qubit. That means x1 and x2. Alright, expression remains the same. Now if you solve little further, you can just combine this minus 1 with this minus 1 and you will get in the exponent x1 y1 plus x2 y2. Okay, and this will be a 2 qubit system. That means 4 eigenstates will be there. So x dot y, basically x dot y is a dot product of the vector components. What are the vector components? x1 y1, x1 y1, x2 y2 are the components of the vectors for x and y. Now we have to extend this expression to an n qubit system. That means we want to know what happens when you apply the Hadamard gate on an n qubit system. Now your cat X is basically an n qubit quantum system, quantum state, and we apply the H superscript cron n. That means we are applying Hadamard on n qubit system, and we have to basically generalize, we have to expand this expression only. You note the coefficient value, it is coming out to be 1 over under root 2 square. I am not writing here 4 because I just want to have a generalized expression, because to this exponent 2 I want to put n, because I am using it for the n qubit system. So it will be 1 over under root 2 raised to the power n. Exactly the same expression comes, which gives the which if you expand this expression, you will get the Hadamard acting on the n qubit system. Now the starting point, again I say, starting point is the Hadamard acting on single qubit, whether it is cat 0 or cat 1. You have to keep track of, if you are applying Hadamard on cat 0, you will get a plus sign here, cat 0 plus cat 1. So plus sign is there. Once you apply the Hadamard on cat 1, you will get a negative sign. So that you have to just take care of, and that's why these we are actually deriving these expressions so that we should not miss this negative sign. Now in quantum computing, sometimes we have to write a different equation than this equation number 1. This is because we write this equation because we usually start with the all zero state. Normally the quantum system is initialized with the all zero state. So that is why we write a simpler form of the equation number 1. Now if we are starting with cat 0 state, that means the starting state is cat 0. In that case, to our advantage, we need not to take care of the negative sign, because we know that if we are applying the Hadamard on cat 0 state, whether it's a 2 qubit, 1 qubit or n qubit system, we need not to worry about this sign, because we will get the plus sign. So therefore this becomes easier for us. This shows the Hadamard acting on cat 0, that's an n qubit system, and you will see that there is no we are not taking care of the negative sign, because we know that the negative sign will not come. So this is the reduced expression if we are starting with all zero state. So this is all about the multi-qubit quantum systems. Thank you very much.